Now, in these cases, lasso doesn't perform very well. Why it doesn't perform very well is not actually due necessarily to lasso, it's due to the instability of OLS, which is caused by this collinearity. The point is lasso doesn't help in these cases, but ridge actually does help. It stabilizes the solution, and we'll see why later on. We'll see exactly why. And so lasso and ridge can be combined to take the advantage, combine the advantages of both the sparsity of lasso and the stabilizing effect of ridge into what is known as elastic net. Right? But in order to appreciate that fully, and it's time anyway, we're going to first look at how we solve the lasso problem. So now we're going to see precisely why we get sparsity, precisely in mathematical terms. So it's absolutely clear. There's no ambiguity about it. There's no wishy-washy, hand-wavy pictures. It will be very, very precise. And then we will see what lasso does, or actually more to the point, what it doesn't do, which ridge does do. Right? So now we're going to move on to the proximal map solution for lasso. And in order to do this, I'm going to have to explain a few things because even though this is all in the optimization videos, I'm guessing some people won't watch those. So I will just reproduce here the key bits of information that we need in order to develop the proximal map solution. Starting with what is a convex function and what are its properties? Why are convex functions so nice? Why do we like them in optimization theory? So the definition of a convex function is as follows. So we're considering only functions of that are real valued, so they map to R. So let's say we have a function of theta defined on some set theta, and we pick any two values arbitrarily of theta in this set. Let's call them theta 1 and theta 2. And we define some parameter or variable t that ranges from 0 to 1, including 0 and 1. Then for a function to be, or this function to be convex, we need to satisfy this condition, that the value of f anywhere along this line segment is less than or equal to this line segment. So here we have a line segment in input space, in theta space, and here we have a line segment in output space. Now, what does this mean geometrically? Well, let's have a look at an example where theta is real valued. So these thetas are real values. So this is just some subset of the real line. So it's a function of one variable. F is a function, real value function of one variable. And let's have a look at this example here, theta squared. So here is our function, right, theta squared. So this line segment here would lie along here. So this value here would be, let's say, theta. Ooh, why is that doing that? Theta. Give me a second. Okay. So let's start that again. This thing seems to have a mind of its own. So this point here, let's say this is theta 1, and this point here is theta 2. So we're defining a parameter t such that along this line segment in this input space here, we go from at t equals 0, we're going to get theta 1, because this will be 0, to t equals 1, where this will become theta 2, and this will become 0. So we'll go from theta 1 to theta 2. And what will this do? Well, this will take us from here, f at theta 1, to here, which is f at theta 2. So this is a line segment. So this is a line segment in our input space, and this is a line segment in our output space as you go from t equals 0 here to t equals 1. We go from here to here, and we go from here to here in the output space. Now, what this means more intuitively is that if we were to take any 2 points, theta 1 and theta 2, so let's take this value here, theta 1, and this value here, theta 2, and draw a line in this 2D case between this point and that point, this we call a chord, then this chord has to lie entirely above the graph of our curve, right? So this function has to lie entirely above the function values. So the function value is always less than or equal to, it can lie on this chord, but it can't lie above it. So this here has to lie below, this chord. And this must be true for any chord. So I can pick another value here arbitrarily. Let's say that value, this value here, all right? And let's say another value here. And again, if I connect these two with a chord, this function from here to here, from this value of theta to this value of theta, this would now be my theta 2, and this would be the theta 1, has to lie below. And that's true for any 2 thetas that I picked, right? Any 2 thetas I picked within some set theta. So in this case, f theta is equal to theta squared, we have a convex function. So this is what I mean by curves upwards, right? It's a function that curves upwards. In this case, we have a non-convex function. So this is non-convex. Non-convex. Why? Because we can take this value of theta here, let's call that theta 1, and let's call that theta 2. And we have this line segment here, and the line segment going from here to here, these function values. And this line, this chord lies below the function at those 2 points, theta 1 and theta 2. Right? So this, the function, the graph of the function lies above this chord in this region. Here we're fine, and here we're fine. But here, from here to here, we have a problem. So this is a non-convex function. It's curving downwards in this region. So the opposite of a convex function, what we call a concave function. Right? That's the and we can always, concave functions are also okay. They're nice because minus a convex concave function will be a concave function, or minus a convex function will give us a concave function. So it's nice when we deal with either convex or concave functions in optimization theory. It makes it easier. You can see here why. Why does it nice? Intuitively, you can see why, because here we have a unique minimum. Here, we have one here and one here, and we have a maximum there. Right? So these situations are always much easier to deal with than these situations. Okay, now the empirical loss, which we define like this, well, strictly speaking, there's a 1 over n there. There's 1 over n times this, is a convex function. Convex as a function of theta. It's quadratic. Any quadratic, and this is a quadratic in theta, is a convex function. So even is the L1 loss. The one norm loss is also convex, but it's not differentiable, and that will be key to developing our proximal map solution. Now here is an important fact. So I'm just picking out the most important facts that we need in order to develop this proximal map solution. A function f of theta is convex in some set theta if and only if this relationship is true. So at any point theta 1, we can approximate, we can upper bound the function. So at theta 1, we can upper bound the function by this quadratic. This is a quadratic upper bound of the function at theta 1. And what is it? It's just a first order Taylor expansion, right? In multivariate case, where theta is not a scalar but a vector. So this is an upper bound on the function. All values of the function at any theta 2 locally near theta 1 satisfy this. provided f is convex. And, and that's true for any value of theta 1 that we choose. So this is one thing that makes convex functions so nice. And you can see why this is true from the diagram I drew on the previous slide. It's always curving upwards. Right? So what does this inequality tell us? Let's be a little bit more precise via a 1D example. It's telling us that this affine approximation, so this is the bias term and this is the linear part of our function f of theta, right, at some point theta prime, is a lower bound on f of theta. Right? So because f of theta is going to be, so if we replace theta 2 with theta and theta 1 with theta prime, f of theta is going to be greater than or equal to f theta prime plus the gradient of this transpose theta minus theta prime, which is exactly what I've written here. So this affine approximation of our function locally around theta prime is a lower bound on the function theta locally. So let's have a look at an example of that. So we'll again pick this example of f theta is theta squared, which is convex. And let's pick this point theta equals 2. Right, so I'm picking here the point theta equals 2. This pen of mine is doing crazy things today. Okay, so let's pick the point theta equals 2. Right. So picking this point here, theta prime equals 2. Theta prime equals 2. What we're saying is that this affine approximation, which is a first order Taylor series expansion of our function around here. So in the case of, so here we've got only one where theta is a scalar and our function is, so our affine approximation is going to be the function f at 2 plus the derivative of f, because there's only, the theta is a scalar, so it's df by dx. Let me write that out. df by dx by the theta at theta equals 2, right, times theta minus 2. This is our affine approximation. The function f of theta squared will always lie above this here at this point. So what does this look like? This is going to be f at 2 plus df by d theta is 2 times theta, right? So it's going to be df, this is 2 theta at theta equals 2 times theta minus 2, right? So 2 at theta is going to be, well, I've just put, I put here f prime. Here I put f prime at 2, right? So that is f prime at 2. This is going to be 2 times 2. So this will be 4. 4 times theta minus 2. That's a bit more explicit. And f at 2 is going to be 2 squared, which is 4. So it's 4 plus 4, so it's 4 into 1 minus theta minus 2, right? Which is, let me make sure I've got this right. It's going to be, there's no point putting, is there any, yeah. So it's 4 times 1 minus 2, so it's going to be 3 minus theta, right? So this is what it is. Is that right? So theta equals 2, we're going to get 4, right? 3 minus 2 is 1 times 4 at 2, yeah, 4. So it's this. 4 times 3 minus theta. It's more explicit what this is. So the point is that this affine approximation is always below, it's a lower bound of our function f theta equals theta squared, right? And so this affine approximation is somehow supporting this function, right? This function always lies above this affine approximation, right? Which is what I'm saying here.
So this affine approximation supports the function in some sense. Now, what's an important consequence of this? It's that this is a sufficient condition for a unique global minimum if f is convex at some theta star, i.e. f of theta is greater than or equal to, because if f is convex, we have this relationship for any theta and theta star. Theta star is the minimum. F of theta is going to be greater than or equal to f of theta star plus this transpose of the gradient times this. Well, if this is 0, then this is just going to be f of theta star. And so f of theta for any theta is greater than or equal to f of theta star. So this equals 0, gradient equals 0, 0 gradient is a sufficient condition for a unique global minimum, because this is true for any theta and theta star, right? And so this condition, which we call first order optimality, is enough. We don't need any second order information. So in optimization, gradient-based optimization, where we use gradients or derivatives, first order optimality is basically in 1D, d by dx of our function f is 0. Right? This we call first order optimality. At any extremum, maximum, or minimum, we need to satisfy this condition. And then we have second order conditions. Is it a maximum or a minimum? We need to look at the second. If that is negative, we have a maximum. If it's positive, we have a minimum. Right? Here with convex functions, this is enough. Right? So this is enough, or in the multivariate case, this would be the gradient of f equals 0, the 0 vector. This is enough. We don't need to know what is the second derivative. And the second derivative in this case would be what we call the Hessian matrix, right? Which is somehow related to, it's a measure of curvature. If we consider the eigen directions of the Hessian, but we're not going to do that. Not here. That's all explained in the multivariate vector and matrix calculus videos. So we don't need second derivative information. This is sufficient. We just need to satisfy this. So this makes convex problems, well, one of the things that makes them nicely behaved, and why there's so much optimization theory devoted specifically to convex problems and then categorizing convex versus non-convex. Now, that doesn't mean that we can't solve non-convex problems. We can, right? We just have to use somewhat different tools, more tricks. Now, classical machine learning relies on the convexity of our penalized risk. So the penalized risk is our r hat n, which is a function of theta. This is convex, plus some penalty. Right? So normally that's a norm penalty. So it's in some norm of theta, right? Some norm. I'm not going to specify which one, times some lambda. And this also is convex. So both are convex. So we've got a convex plus a convex. The whole thing is convex. This is our objective. This is what we want to minimize, right? Penalized empirical risk. And all of these are essentially a penalized convex risk. The whole thing is convex. So support vector machines, which we will look at in great detail, which we'll develop from a dual optimization point of view. We'll look at KKT conditions, logistic regression, which we're also going to look at before we look at this, ridge regression, which we've also seen, lasso, and kernel ridge regression, which we're also going to look at in non-parametric methods, as well as support vector regression, which is the regression version of support vector machines. And these all, as I say, rely on the convexity of this penalized empirical risk.